Welcome to this episode of the CompTIA Tech Plus Prepcast by baremetalcyber.com. Let's begin. The computing cycle in digital systems follows a logical flow of input, processing, output, and storage. This sequence is at the heart of how every computing device, from a smartphone to a supercomputer, interacts with users and data. On the CompTIA Tech Plus exam FC0-U71, you may be asked to recognize or describe each stage, as well as understand how they connect in real-world scenarios. Mastering this cycle will strengthen your understanding of concepts in later domains, including infrastructure, software, and troubleshooting, because it explains the foundation on which all computing operations are built. In computing, input refers to the act of feeding data or commands into a system, so it can act on them. This is the very first step in the computing process, and without it, no further operation can occur. Input can be as simple as pressing a key on a keyboard, or as complex as reading sensor data from an automated manufacturing system. Knowing how to identify and classify different kinds of input will help you understand system functionality and the role of peripheral devices in the overall process. Common input devices and their use cases vary based on the environment and the task being performed. Keyboards are used for typed commands and text entry, while mice and touchpads provide point-and-click navigation in graphical user interfaces. Microphones capture audio for voice commands, video conferencing, and content creation. Scanners and cameras convert physical information, such as printed documents or images, into digital data that can be processed by a computer. Recognizing these devices and their roles is essential for identifying how input enters the system. Processing is the stage where raw input is transformed into meaningful output. This involves calculations, logical operations, and command interpretation. The Central Processing Unit, or CPU, handles most of this work in general-purpose computing systems. Other processors, like graphics processing units or GPUs, take on specialized tasks such as rendering images or handling parallel computations. Whether it is a simple arithmetic calculation or a complex simulation, the processing stage determines the quality and speed of the output. The CPU is often called the brain of the computer because it executes instructions from software and manages the flow of data through the system. Clock speed, measured in gigahertz, indicates how many cycles per second the processor can execute, which impacts performance. Multi-core processors can run multiple tasks simultaneously, improving efficiency for multitasking and compute-heavy applications. The capabilities of the CPU influence the overall performance of the system across all types of workloads. Random access memory, or RAM, plays a critical supporting role in processing. RAM stores data temporarily while it is being used, allowing the CPU to access it quickly. More RAM typically improves multitasking capability and speeds up processing by reducing the need to retrieve data from slower storage devices. Because RAM is volatile, its contents are lost when the system is powered off, which is why permanent storage is also required. Output is the stage where processed information is presented to the user or sent to another system. This completes the computing cycle by turning processed data into something that can be understood, acted upon, or further used. Output can take many forms, including text, images, video, audio, or even mechanical movement in specialized systems. Without output, the results of processing remain invisible to the user and have limited practical value. Output devices bring the results of processing into the real world. Monitors display visual output such as user interfaces, documents, or videos. Speakers produce sound from digital audio files or system notifications. Printers convert digital documents into physical form, while projectors and smart televisions display visual content on a larger scale for presentations or entertainment. Knowing these devices and their functions will help you understand how systems communicate with users. Storage is the stage of the cycle that retains data for later access, whether for seconds or for years. It includes both volatile forms, which store data temporarily, and non-volatile forms, which retain data even when powered off. Stored data may include user files, application software, system settings, and operational logs. Reliable storage ensures the continuity of operations, user data availability, and access to software resources when needed. Primary storage is the immediate memory a system uses during operation, such as RAM, while secondary storage refers to devices like hard disk drives, solid-state drives, and removable media. Secondary storage retains data without power and holds the operating system, applications, and long-term files. Systems use both forms to gather primary storage for active tasks and secondary storage for permanent data retention. Hard drives and solid-state drives are the most common forms of secondary storage. Hard drives use spinning magnetic disks to store large amounts of data at relatively low cost, while solid-state drives use flash memory for faster, more reliable storage with no moving parts. Solid-state drives are preferred in most modern systems because they offer better speed and durability, but both technologies store operating systems, files, and applications for everyday use. Cloud storage extends the concept of secondary storage to the Internet, allowing data to be stored on remote servers and accessed from multiple devices. Services such as OneDrive, Google Drive, and Dropbox provide file syncing, remote access, and backup capabilities. Cloud storage plays a role not just in user convenience, but also in infrastructure, enabling data availability and collaboration for businesses and individuals alike. The interplay between the four components, input, processing, output, and storage, ensures that computing tasks are completed successfully. Input feeds data into the system, processing interprets and transforms it, output delivers it to the user, and storage retains it for future use. A weakness or failure in any one of these components can degrade performance or stop operations entirely. Technicians and support personnel rely on an understanding of this cycle to diagnose and optimize systems effectively. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Examples of the full computing cycle make it easier to see how these four elements work together in real situations. Writing a document begins with input from a keyboard, moves to processing by the CPU to apply formatting and update the display, produces output on the screen so the user can review the text, and ends with storage when the file is saved to a drive. Streaming music starts with the user's song selection as input, involves processing to decode the audio file, produces output through speakers or headphones, and may use storage to cache the file locally for smoother playback. Recognizing these patterns helps you quickly identify each stage in both exam questions and real-world troubleshooting. Mobile devices follow the same computing cycle, even if their form factor and hardware are different from desktops or servers. A smartphone uses touchscreens and on-screen keyboards for input, mobile processors for running applications, and high-resolution displays or speakers for output. Storage can be local in the device's internal memory or remote in the cloud for access across multiple devices. Understanding these similarities makes it easier to apply computing concepts to any platform, whether it's mobile, desktop, or embedded. Embedded systems and Internet of Things devices operate on a simplified version of this cycle. A smart thermostat, for example, takes temperature readings as input from built-in sensors, processes those readings with a small, efficient microcontroller, produces output by adjusting the heating or cooling system, and stores usage data locally or in a connected cloud service. These devices may not have a traditional user interface, but the same sequence of input, processing, output, and storage still applies. Troubleshooting using the computing cycle is a structured way to find and resolve issues. If a user reports that nothing happens when they press a key, the problem could be in the input stage, such as a disconnected keyboard. If an application freezes, the issue might be in the processing stage, possibly due to insufficient memory or CPU overload. If there's no sound, the output stage may be at fault, such as muted speakers or faulty audio drivers. If files can't be saved, storage could be full, failing, or misconfigured. This methodical approach reduces guesswork and speeds up problem resolution. System performance depends on the speed and quality of each stage of the cycle. High-quality input devices improve accuracy and accessibility, which matters for productivity and user satisfaction. Faster processors reduce waiting times and handle more complex tasks, improving responsiveness. Adequate and fast storage ensures quick file access and prevents slowdowns caused by disk bottlenecks. A balance across all four elements is important because a weak link in one area can limit the performance of the entire system. The computing cycle has remained consistent even as technology has evolved dramatically. Early computing relied on punch cards for input, vacuum tubes for processing, cathode ray tube displays for output, and magnetic tape for storage. Today's systems use touchscreens, multi-core processors, high-definition displays, and solid-state drives, but the flow of input, processing, output, and storage is unchanged. Knowing this history helps put modern devices into perspective and can also clarify why certain legacy systems work the way they do. Security must be considered at every stage of the cycle. Input can be compromised by keyloggers or malicious USB devices. Processing can be targeted by CPU-level exploits or vulnerabilities in software logic. Output devices can unintentionally expose information if they are unsecured or publicly visible. Storage needs to be protected through encryption, backups, and controlled access to prevent data loss or theft. By viewing security through the lens of the computing cycle, you can identify where protective measures are most needed. In real-world IT work, professionals interact with each stage of the cycle daily. Help desk staff troubleshoot broken input devices, misconfigured output settings, or slow processing speeds. System builders balance specifications across components to meet performance goals. Network and system administrators monitor storage health, plan upgrades, and ensure data availability. Understanding the computing cycle enables more efficient deployment, maintenance, and repair across all of these roles. On the Tech Plus exam, you may encounter scenario-based questions that ask you to identify where in the cycle a problem is occurring. For example, a broken keyboard is an input issue, a slow-running application is a processing concern, no display output points to an output device or driver problem, and insufficient disk space is a storage issue. Being able to pinpoint the stage affected will improve both your accuracy and your speed in answering. This domain also prepares you for topics in other areas of the exam. When you study infrastructure, you'll see how input and output devices connect and communicate with the system. In the applications domain, you'll see how processing resources are allocated to software. Security topics will revisit input validation, secure processing, output sanitization, and data protection and storage. This foundation makes it easier to integrate new knowledge as you move through the other domains. Before moving on, it's worth doing a focused review of the key terms and device examples for each stage of the computing cycle. Make sure you can clearly define input, processing, output, and storage. Give examples of devices in each category and describe how they connect in the cycle. Reviewing glossary terms like CPU, RAM, and solid-state drive will also help reinforce your understanding. Practicing identifying the cycle stages in short scenarios will sharpen both your conceptual and diagnostic skills for the exam. In the next episode, we will shift to notational systems: binary, decimal, hexadecimal, and octal. You will learn how these numbering systems are used in computing to represent, store, and manipulate data. We will also explore how base conversions appear in exam questions and how they relate to troubleshooting and system configuration in real-world environments. Thanks for listening. Please visit baremetalcyber.com for more cybersecurity information and education, including a new children's series. For more information on books and more, follow us at cyberauthor.me.